Welcome to the Science for the Public lecture series. Science for the Public is an organization committed to bringing science information and issues to the general public. Visit our website for our program listings and blog.
Good evening. I'm Yvonne Stapp for Science for the Public, and I welcome you to tonight's Contemporary Science Issues and Innovations program. Climate change is a major concern today, and scientists are using a variety of sophisticated means to analyze natural climate cycles over centuries to compare that past history with the present rapid change, which is largely the product of human activity. Our guest tonight investigates climate cycles over millions of years, and one of the best sources of that record, as he's about to explain, is speleothems, the geochemical deposits in Arctic caves. We learn how these natural archives are created and how scientists analyze that unique information. Jeremy Shakun is an assistant professor in the Department of Earth and Environmental Sciences at Boston College. He received his Ph.D. in geology from Oregon State University in 2010, and then was a postdoctoral fellow at Boston University, Woods Hole Oceanographic Institution, Harvard University, and Lamont Doherty Earth Observatory. He joined the faculty of Boston College in 2013. Dr. Shakun is a recipient of the EDU Climate Division Outstanding Young Scientist Award. Dr. Shakun's research focuses on patterns and causes of climate change over the millennia. This information is essential to creating accurate climate models, and in addition to his work on speleothems, he investigates geochemical data from marine sediments and glacial deposits, all in an effort to use ancient geological history to understand better the present and future climate trends. We are delighted to welcome Dr. Jeremy Shakun. Welcome.
Thank you. Good to be here.
Okay. Would you start us off by just reminding us what they call this present condition that we have apparently produced, the Anthropocene? Could you just give us a little background, please?
Sure. So the Anthropocene is basically we hear of the Cretaceous, the Jurassic, these different intervals of geologic history in the past. Well, earth scientists have pretty much realized in the last decade or so that we're in a new era of Earth history. Things are different than they used to be. They're going to be different for a long time. An alien coming, in 100 million years will look at the rocks on the planet and see different things than they would have at any other time interval, and they're going to say something was weird then. And the weird thing is us. It's humans. We are the biggest force of nature now, shaping the whole planet, and that's the idea of the Anthropocene.
So
it's the
it
age of
is us, and also in terms of the climate, that we have produced the present situation. There is no doubt, I think, among scientists,
that humans are the big driver of climate change. There's really no doubt over that basic question. We're the big thing in the room.
Okay, all right. Just to make that very clear, because we do still have some resistance in certain corners. Okay, now we've added all this stuff to the atmosphere, and I understand it will stay for thousands of years, hundreds, thousands of years. We can't just scoop it out right now.
Nope, we can't. A lot of that CO2 is up, and it's going to be hanging around for millennia, like you say.
Okay, because we just want to make that very clear for people as well. In the past, since you have reconstructed the ancient history, CO2 was a factor in these what do you call them, melting and warming cycles, or
ice ages, greenhouse worlds of the past?
Okay, and it was CO2 as well.
Throughout Earth history, CO2 has been probably the biggest knob dialing the global thermostat. Other factors too, but CO2 has been a big player throughout Earth history.
And since you didn't have humans producing it at that time, what was the source?
At different times in the past, different sources. There's carbon in all sorts of different places on the planet.
I see.
Some is locked in oil and coal that we're tapping into today. There's other carbon that's stored in the deep ocean that can vent out towards the atmosphere. There's other big stores of carbon frozen in permafrost in the Arctic. And if that thaws out, that can release carbon. So there's always carbon moving around, and different places it could come from. So different times in the past, it's come from different places.
Okay.
And today, of course, the big place is us digging it up and setting it on fire.
I understand.
Yeah.
Take us back, if you will, for just a second to like ice ages,
Okay.
where you have just an awful lot of ice covering the Earth. Then, and at very deep levels, did volcanic activity, either in the sea or on the land under the glaciers, did that have anything? Could that have been a factor as well?
With the CO2 going up and down? It could have been a factor. People are debating a role for that.
I see.
And I should say the big place we think the carbon went in and out of was the deep ocean.
Oh, okay.
That is the big reservoir that holds carbon, that exchanges with the atmosphere on kind of the 1,000-ish year time scale of ice ages.
Yes, I see.
That said, you bring up volcanoes. That's another kind of hot topic these days scientists are thinking about. And one of the ideas behind how volcanoes might have played a part is that during the ice age, you have huge, heavy ice sheets sitting on the continents, pressing down on them. And once you melt off those ice sheets, it actually releases some of the pressure pushing down on the solid earth beneath it, and it could potentially trigger some more volcanic activity, which could release some more CO2.
Right, and there are volcanoes in the sea, so on the sea floor. So I suppose so. But in any case, the CO2 was the major factor as far as the cycles of melting and freezing. The CO2 was the heating.
I think it was the big factor in sort of warming the whole world up out of the ice age. Yeah.
Okay.
Yep, I think that's fair to say.
Okay. Now, you've done lots of different kinds of work, and we'll talk about that, but take us to the Arctic caves. I think most of us are completely unfamiliar with speleothems and the idea of Arctic caves being this history book.
Yeah. And they haven't been too much yet, but for the last year or two, I've been trying to get up there more and do some work into it. And so caves are a phenomenal resource for geologists to get long records going back in the past, especially from places like the Arctic, where you've had ice ages come and go, and every time an ice age comes and goes, the glaciers scrape away any evidence that's on the surface. So they're constantly erasing any evidence of what happened. But caves are this rare place where it's just tucked down there.
Yeah.
So you can go down there and get some potentially kind of continuous record of here's what was going on the surface of the planet in the Arctic for hundreds of thousands of years across ice ages. So the way a speleothem works, and a speleothem is just a word meaning any kind of deposit in a cave. It could be a stalagmite on the floor, it could be a stalactite on the ceiling, any of those sort of pretty formations you see in a cave.
Yes.
So the main way that these guys work is that rain falls over a cave, and that water seeps down through the ground. It drips, and then bit by bit, it deposits more and more mineral crystals that grow up into these stalagmites. And so basically, the idea here is that the chemistry of the rainwater gets incorporated into the chemistry of the mineral in that stalagmite. So we essentially have this record of the chemistry of how rainfall was changing above the cave as that stalagmite was growing through time. And we can link that back to changes in climate, in temperature, in rainfall, and all sorts of different conditions.
Okay, so presumably this rainfall that seeps into the ground in this way, this carries the signature of chemicals in the atmosphere or at the time. Is that the idea?
That's the idea, and in particular what it tells you about is we look at the isotopes in the minerals, which tell us about the isotopes in the rain, which is controlled basically by climate. If I showed you a map of the isotopes and rainfall around the world, it'd look like a map of climate to you. You'd say, oh my God, it's warm here, it's cold there. You can see it all laid out very, very, very bare.
So if you looked at the Arctic cave or you looked at a tropical, the different caves around the world, it would be a very good record.
That's right, distinctly different. So that's part of the idea. The other angle, the other thing to think about with the Arctic, and I mentioned a second ago, one reason we're interested in the Arctic for the future is it contains a huge amount of frozen carbon in all the permafrost soils up there, which as the Arctic warms more and more, that will be thawed, and that carbon can now burp out to the atmosphere and speed up warming even further.
Right.
But there's a lot of questions over, well, how much warming can you have before you push that too far? How fast might that happen? It's not a simple thing to figure out. So we look to the past to try to figure out, well, when did the permafrost thaw during past warm times?
I see.
And did it take this much warming? Did it take that much warming?
Right.
What drove it? So the way the cave speleothems figure into this is you are only going to form a stalagmite in a cave if there's liquid water dripping in the cave.
Yes.
But if you have permafrost, frozen ground, like you do across most of the Arctic today, there's no liquid water in that ground because it's frozen ground.
Right.
So if we go find some stalagmite in some cave in northern Canada that today is completely frozen,
right,
well then we know that that spot in northern Canada thawed when that stalagmite grew. So if we can date the stalagmite, we can say, oh, here's when it thawed here. And then we can go to a cave over here, and a cave over here, and a cave over here. We can begin to start mapping out when was the permafrost thawing in the past.
Right.
And what was the climate like at the time? How big of a push did it take to get all of that to thaw out?
So you can read a lot by looking at this kind of information, and then various caves tell some different stories in different regions.
That's right.
And so on. Do you look for any particular chemical markers?
In the stalagmites? The main thing we're looking at, I guess, are these isotopes of oxygen, which tell us about temperature, and really the growth is really the main thing that we're focused on.
Right.
Yeah.
This work sounds really interesting.
Yeah.
Is it fairly easy to do? I'm thinking here is this stalactite, and you're going to look at layers or something. Is that what you do, or?
It pretty much is. Getting the samples is not easy to do because you're heading way out into nowhere, right? Grizzly bear country.
I was going to say polar bear.
Yeah, that too. That too. So that part's not quick. But then in terms of the actual work, you get a stalagmite out of a cave, and you sort of slice it in half like a sub sandwich.
I see.
Polish it up, and you just see all the beautiful layers laid out in front of you. We go in with a little dental drill, actually, and you drill out a little bit of sample here and there wherever you're interested, and begin analyzing the chemistry to date it, to figure out its age, to look at those isotopes, all of it. Yeah.
That's really quite interesting. How remote are they?
Some of these caves that we have samples from are incredibly remote.
Oh, really?
Way out in nowhere land. I mean, the kind of thing where you're flying into Fairbanks, then catching a smaller plane off into a littler place, and maybe a helicopter from there out into just, out in the backwoods.
That's big territory up in that area. Exactly. Yeah. You have done other kinds of investigations too. I believe, was it boulders from the glaciers and so on? What do you find with those?
So the idea with that work is whenever you have a glacier flowing around, whether it's in New England during the last ice age or in some mountain in Colorado, it's scraping up the land, it's moving, mud and sand and boulders.
Right.
And when it melts out, it just drops those boulders. So what we can do is we can go to a boulder today that we say, oh, that was dropped by a glacier. Well, when did that happen? We could date when that happened by knocking off a chunk of the rock. And we measure the chemistry of the rock, and we can use that to basically figure out the age of when the ice dumped that boulder on a landscape. I
see.
And so that's something that people sort of do all over the world, and that I've spent a lot of time trying to put together to understand the history of glacier fluctuations.
I would never have thought that this was such a gold mine of information, these boulders, and they're everywhere. They're in New York, they're around here. You can see that they're everywhere.
That's right.
Where there were glaciers.
That's right. And so the way this works is it's actually pretty simple. It's so there's cosmic radiation coming from deep space all the time, hitting you, me, the table constantly, and also hitting boulder surfaces. So the interesting thing that happens is when it hits say a chunk of granite that's got some quartz in it, cosmic ray hits some quartz, and it produces the isotope beryllium-10, which is a very rare isotope otherwise. And the longer that boulder is sitting out there, the more it's getting cooked by cosmic rays, the more beryllium-10 builds up. And so we go and we knock a sample off, we bring it back to the lab, and we know how fast this stuff is produced. So if we measure how much there is, we know how fast it's produced, we can figure out how long that boulder has been sitting there. So that's the basic idea. It's sort of like it's like measuring the sunburn on boulders all over the place.
Amazing. And that's a very good way to put it. I guess I wouldn't have thought of that, but and there's so many of them. So you can get the age of the rock, I guess the origin many times too, because they get carried such distances and stuff, but above all the age, and it gives you this climate information as well.
Right.
you've looked at other kinds of information as well. Have you looked at like ice cores? I know that, well, I want to ask specifically about the Antarctic cores.
Yeah.
They've gotten lots of attention, but
Yeah, so I haven't gone to Antarctica myself and done the 4 months out there pulling up the ice, but I spent a lot of time looking at the data from those iconic cores. Yeah.
Right. I think that you had something interesting to say about this because much has been made of the Antarctic ice cores, and in some cases maybe information has been distorted, not by the scientists, but by climate deniers and stuff. Can you give us a little background on that, what those cores tell you and how it could get mixed up?
So the amazing thing about these ice cores from Antarctica, so Antarctica is covered by a huge ice sheet, a couple miles thick. People have gone down there, scientists have gone down, and they drill a cylinder of ice through the ice sheet, and you get layer upon layer of essentially old snowfall as an ice core. And you can measure basically what the temperature was doing through time as that snow was falling. Same idea we mentioned with the speleothems. So you can measure what temperature was doing back through time in Antarctica, and you can measure the amount of CO2 in little air bubbles that are trapped in those ice cores back through time. So you get a record of temperature going up and down over ice ages, and this record goes back almost 1 million years from ice cores. Amazing. So you get a record of temperature over the last 1 million years, you get a record of CO2 over the last 1 million years in the atmosphere. And the amazing thing about it is you plot these two together, and CO2 and temperature for 1 million years, and it's just the two of them together.
Isn't that
it's just lockstep.
Right,
Lockstep.
right.
Science almost never works out so beautifully with such a perfect, but there it is right in front of you. So you look at that and you start wondering, there obviously temperature and carbon dioxide are connected throughout the ice ages, but how exactly are they connected? And so I guess a point that's often that you're alluding to here is a lot of people will look at that and say, oh my God, look, clearly CO2 is driving temperature up and down just like today. Well, it turns out if you look really closely at that record at any given event, there's some uncertainties and some error bars, but you could make an argument that maybe the CO2 or the temperature is warming up just a little bit before the CO2 starts rising. And so a lot of folks have said, oh, there you go. Look at everybody's getting it backwards. It's not that CO2 causes warming. It's that warming causes CO2 in the past. And maybe it's doing the same today. And maybe this whole CO2 thing is bogus. So so I've spent a lot of time looking at this issue. And the key thing to know about this ice core record is that the CO2 measurements it gives you in these little air bubbles, that CO2 level tells you the CO2 of the whole global atmosphere everywhere. And that's because CO2 is basically the same everywhere. I mean, we emit some CO2 or it comes from a volcano, give it a few years, the winds mix it, it's the same everywhere. So that's a global record. But this record of temperature from Antarctica is like a record of temperature from anywhere. It tells you about temperature there.
That's it.
So you got to be careful to try to take the record of temperature from one place to say something about global climate change. And when we're thinking about greenhouse gases and their effect on the climate, the relevant thing to think about is, well, what is it doing to the global climate? That's really the meaningful metric to use. So I spent a good chunk of my dissertation looking at all sorts of other temperature records we have from around the world, because we don't have just records of temperature from an ice core in Antarctica. We have them from ice cores in Greenland, or from ocean cores all around the world, or from lake sediment cores, or all sorts of different techniques people use. And we pulled all of these records together from all over the world, slapped them into a global average temperature, and what do you know? Over the end of the last ice age, the global average temperature rises right along with the CO2 and just after it. Just kind of like you would expect if CO2 is the main thing pushing the temperature up.
Right. So that was quite a little breakthrough, because I realize that other argument has been used and still is, but you've put the end to that. The other thing that you mentioned is the varieties of data, the marine cores, the ice cores, the caves, all of this stuff. It's also a great deal of data.
Oh yeah, in the geologic record, all the information that's been amassed, it's a huge amount.
What are you doing? I mean, that must be incredibly difficult to put together and share out.
a big global data sets of information?
Yes.
It is.
That must be a project in itself, is what I'm...
It's projects upon projects.
Uh-huh.
But there's a lot of data out there in the world, and I think that's a key piece with climate science in general. For today or for a million years ago, it's a big, complicated global climate system.
Yeah.
The only way you're ever going to make sense of any of it is to pull 1,000 or 1,000,000 data points from the whole world all together so you can see the big picture.
Yes,
I think that's one of the challenging things with climate change is we're always so inclined to look at one little spot or one little moment in time, but you need all that data on the table.
And that you need huge amounts of data probably to make the models. Is that the case? I mean, are your models better as a result of having this huge amount of data?
Absolutely. Absolutely. So you need data always to test models.
Right.
Right? We use our best physics and understanding of how the climate works, put that into equation form and try to model it, but you end up with a result and you say, is that good? Is it not good?
Yeah.
Who knows? Well, take your model, try to simulate a past ice age, try to simulate some other climate event and see, can we actually get this model to reproduce what we see in the ice cores, in the ocean cores, all those different features. So it's a key test to see if computer models can capture a big climate change accurately.
It's quite amazing. Two things. First of all, that climate is so complex, so dynamic. Would like to ask you about just trying to work through anything so complex. And the other is scientists who do, say, marine cores, are they learning to read ice cores or speleothems and things like that?
Yeah, so I think that so you're right. I mean, you're right. It's amazing the number of ways you need to approach the problem to fully understand it.
I wonder.
And so I think what you really have out there is what you should have. You have a whole kind of spectrum of different scientists. Those who focus, on the incredible details of a particular technique, to the modelers, to sort of generalists in between who can help translate among the different groups.
So you do have to have translators.
You sort of do. You do. But I think actually the science, I think paleoclimate science has actually shifted more towards kind of a holistic view over the past, 10 or 20 years.
Especially maybe younger people coming up.
And I think younger people like me sort of saw that trend happening, and that's part of where I jumped on board that train because I think in decades gone by, it was, the first days of getting ice cores. Well, then you need a whole community of people to just figure out how the heck do you get an ice core? What do you do with this thing?
That's true, yeah.
But I think at this point, there's a lot more integration going on. And I go to a lot of conferences and meetings and workshops where you have ice core people and ocean people and computer people and modern climate people and all sorts of cross-pollination trying to put it together.
They do make an effort to put it together, right. The other, another thing here, you train students now, so are you training them in this more comprehensive, more holistic approach? Do they sort of have to learn everything?
They have to learn a bit of everything, I would say.
Yeah,
a little bit.
right.
I mean, it's always kind of a careful dance between not spreading yourself too thin.
Right.
And I think for different people, they're going to want to take different paths along that, along that spectrum.
Exactly.
But sure, students who work with me, I really sort of like that general perspective and trying to pull different threads together. So I think that comes through in my work with them. But you always want to make sure that something I'm really emphatic about is making sure I'm always collaborating with the specialists who know the ins and outs and every last detail of a particular technique or indicator or lab measurement or whatever it is. You make sure it's all kind of being brought together.
Just out of curiosity, the technology, I guess that's what you'd call the tools that you are able to use today, seem to have developed a lot. Is that true? Are they very good as opposed to, I don't know, even 30, 40 years ago? I have no idea.
Absolutely. Absolutely. All sorts of measurements that we can make today that never were possible in years gone by.
Yeah, example.
Yeah, so one of them is these Arctic speleothems I'm working on. A lot of the samples that I have are from scientists who collected them in the 70s. And they were doing all this work in Canada, and they had all these stalagmites from back then. But they weren't able to do that much in terms of analyzing it because they just didn't have the technology. The uncertainties weren't small enough to be able to make the measurements you would need to make. And so anyway, in the last couple of years, I've made friends with them and said, hey, can I take a stab at those. And they said, of course, this is ripe for the new technology.
Yeah.
And so now we're remeasuring things that they had first taken a stab at 40 years ago, but whereas it was a sample that they would get an error bar like this, or they couldn't even measure, we're now,
Wow.
down here.
The technology has gotten so good that it leaves no doubt at this point about the human factor here contributing to the present situation, just because you have such
good
solid
technology,
information.
data coverage.
Right.
Yeah, and I think the other thing that we have that you kind of can't stress enough with sort of modern human-caused climate change is that the argument for anthropogenic climate change isn't like it rests on that piece of evidence or that piece of evidence. It also rests on that piece and that piece and that piece and that piece and that piece. And
Yes.
it's a whole kind of complex of
Okay.
different independent lines of evidence all together, which is why I think you have almost every climate scientist looking at it
Right.
saying,
That's just, they say
okay,
it's
that's kind of-
100%
there you
anymore.
go.
Right. No more questions. Isn't it interesting that for decades you could keep up this doubt business, much of it deliberately generated, but I mean that there, in some circles, there were legitimate scientists who had questions about it. They don't anymore. There is one more thing I've meant to ask about. One of the favorite excuses for the deniers was about the Earth's regular tilting. What is that called, and how does that figure in this?
Yeah, so the Earth's orbit around the sun isn't static. It slowly changes through time. The Earth's axis sometimes tilts a little more, a little less. It sometimes wobbles this way. The orbit around the sun isn't always a perfect circle. It stretches out, it comes back, it stretches out. And so all of these different, what we call orbital cycles, or Milankovitch cycles for the scientist, who's kind of credited with really thinking deeply about them. All of these different cycles seem to be responsible for tipping off ice ages to come and go. And we talked before about how CO2 was really important for the ice ages, and it seems like CO2 was really important for bringing the whole world in and out of ice ages. These Milankovitch cycles tilt the Earth this way, that way. They kind of redistribute who's getting more sunlight. More sunlight here, more sunlight there. It doesn't change the global amount, but it kind of redistributes the sunlight across the world. And so, sure, these orbital cycles seem to have been important for causing gigantic ice ages to come and go, so maybe the warming of the last 100 years is due to these orbital cycles. There's a lot of flaws in that logic, but the simplest, most obvious thing to point to is that these cycles are incredibly slow. They happen over 20,000 years, 40,000 years, 100,000 years.
Not since the Industrial Revolution, right?
In the last 100 years, these cycles have done that, right? It's not.
Well, that was a bad argument in the first place then, really, wasn't it?
It was a bad argument in the
around
first place.
for a long,
Sure.
It was invoked frequently by some who were in the denial business. But thank you for straightening us out on that. In terms of your work broadly, you've done a lot of different things. Do you have a favorite area?
Oh, I guess you mean in the world, or in terms of?
Well, I meant a specific, like the speleothems or the cores, or do you like putting it all together? What do you like the best, modeling?
I don't actually have a favorite area. I find that I like a little bit of all of it.
Yeah.
As a scientist, I find that it's easy to, do you do the same thing day after day after day after day, and I start to find that after a week or a month I say, wow, I need something different. And so it's really fun to bounce over here and be behind the computer more.
The right field for sure.
So I find that it keeps it fresher to sort of, be mixing in multiple different pieces.
Yeah.
Yeah, absolutely.
And I was going to say, is there any particular sort of data, the speleothems and so on, that is, in your mind, the best source?
Probably not.
Okay,
probably
they all
not.
offer
They
something.
all offer a different lens. I mean, so we're using ice cores, we're using old layers of snowfall, old layers of mud, old tree rings, all of these indirect ways to try to get some lens, some perspective on a snapshot of climate in the past.
Yeah.
And they've all got advantages, but they all have different quirks and issues you could imagine by trying to use the width of a tree ring to tell you about the temperature. Well, other things affect trees, right?
Right,
Well,
right.
same thing is true with layers of snowfall or mud on the seafloor or stalagmites in a cave. And so, I think really the strong way to come at this is you use this, you use this, you use this, and you pull it all together. And when it tells you a big, consistent, coherent story, you go, there it is.
Wow,
Now that's getting
that's
solid.
satisfying.
Right.
Right. In terms of how old, how far back something can go, like the tree rings,
Right.
I think are limited.
Sure.
I don't know about the marine sediment cores and stuff. Is one of those, can it be a longer record? You know what I mean?
For sure. For sure. Each one gives you a different sort of, again, advantage. So tree rings are great if you want to study the last, few hundred years. I mean, you're not going to find that many trees that are 100,000 years old. Ocean sediments, there's been mud piling up on the seafloor for millions, hundreds of millions of years. So that's great for that. If you want to go even further back in time in Earth history, you want to go back 1 billion years ago, 3 billion years ago, now you got to go look to old rocks. And so everything you look at gives you a different lens, further back in time, or maybe, a higher resolution with more data points in time. It depends kind of on the question you're asking.
I see.
But there's usually a tool for whatever the question is you're asking. You just got to find the right tool that's going to give you the information to kind of get into that issue.
Right. What an exciting field.
Yeah.
Today, especially.
It's a blast.
Sounds like.
It is a blast.
I bet.
I love it, yeah.
And you like to get out there with the polar bears and things anyway, right?
You gotta.
Yeah. How did you ever get into this in the first place? Did you just, as a small child say, I know I'm going to be a climate scientist when I grow up?
I didn't quite know if I was going to be a climate scientist. I kind of always maybe thought I kind of liked the meteorologist thing, the weatherman thing. I think I always sort of, the guy who's getting up there and talking about the cold front coming in or something.
I know, with assurance, but it was wrong.
Yeah, well, right. I always sort of like that thing. If there's nothing on TV ever, I was always popping on the Weather Channel and kind of just like, this is fun to watch. I like this sort of thing. But other than that, I guess I got into this because I just always loved science. Just always curious about the world, how it worked, and so I was always into that. And I always loved hiking, always loved nature, always liked the idea of heading off into the backwoods of Alaska. And you put these things together and you pretty much wind up at earth science. And I always love the weather, so if you're going to be an earth scientist who likes weather and climate, well, then you're pretty much going to end up being a paleoclimatologist using earth history records to look at climate in the past.
Right,
Yeah.
but it involves so much. There's the chemistry of it, the geology, I don't know, it's really comprehensive.
It's mind-boggling. It's absolutely dizzying when you think about all the different pieces that are involved in the climate. You need to know things about biology and oceanography and chemistry and the physics of the atmosphere and ice and how it flows and all these different pieces together. So it's gigantic, which makes it fun.
Right.
But also, huge.
On that, because it seems as though this might require a certain type. In much of academe, generally, people tend, as we said, to be quite narrow, but you stay in something forever. You don't have to keep studying. But in your field, it seems as though you're learning something every 10 minutes, and you need to stay abreast of all this new information. Is that true? And do you think it takes a type?
Yeah, I think that is true. There is always more information coming out. There's always new things, and so you always pretty much need to keep up to speed on that. Because if you haven't kept up with the latest research for the last 5 years or 10 years, then you need to sit down for 4 months and get to it. Because if you don't, you're going to be behind.
Lost,
You got to have it, so you know where we're at, what the right question is to ask. Now you're always getting deeper into these questions.
Right.
So I think you definitely need that.
Right.
Yeah.
And one more thing in terms of climate, what's your prediction for the future in terms of the globe? What can we take? How much worse is it going to get?
So the biggest control on how much more warming and overall change to the climate we see comes down to how much more carbon we emit primarily. That's the single biggest thing. CO2 is the biggest knob cranking up the thermostat. How much more do we raise it? A little bit more and sort of wean ourselves off fossil fuels in the next 20, 30, 40 years? Or is it just...
Which can be done.
Which maybe can be done, yeah. Or is it sort of pedal to the metal? Forget about it, boom, we're going through this century and beyond with fossil fuels. And if we do that, well then CO2 is going up to here. And what I can tell you for sure is if you go back in Earth history, the last time CO2 was up here, it was an unrecognizable world. I mean, completely different. People always say, well, CO2 was higher in the past, which is true, and it was a completely different world in the past.
What was the world in that time? What was alive?
Yeah, well, it was very different in terms of biology, but if you raise CO2 3, 4, 5 times higher than where we started, you're going to get rid of most of the ice on the planet, which means sea level is going to go up a couple hundred feet.
Right.
So redraw your maps of coastlines around the world, because that's gonna come in.
Yes.
That'll take time to fully unfold, but that'll be locked into the
But
system.
it already seems to be accelerating faster than people had predicted, even given the conservatism of trying to
I think that's right. I
not
think that's
be
right.
an alarmist or anything.
No,
but they
I
are
think in general that's right. I think we had, if you look at the evolution of the sort of the scientific predictions, I think we have, on the whole, tended to have too much of a sort of a linear perspective on the Earth system, and kind of thought it's a little more stable and it moves very, simply and linearly. And I don't think that's quite the way it maybe actually works. And I think when we look at a lot of Earth history, we see that that's not necessarily true. It can do all sorts of, wild, jumpy things.
Yes. Yeah. Right. So no matter what happens, if we could switch to renewable, do all the right things tomorrow, we would still have this warming continuing for significant warming now that we can't reverse. Is that the idea?
We have a few more decades kind of baked into the system of warming. Just like when you turn the thermostat up, if we crank the thermostat up right now,
right.
Well, wait, because there's still another 20 minutes before the room fully warms up. It's going to take time. Well, the planet's even bigger, so give it decades of more warming locked in. And if there's more warming locked in, well, ice takes a long time to melt, and so we have huge ice sheets in Antarctica, huge ice sheets in Greenland. You crank the temperature up a degree or 2 or 3, you're going to melt back a lot of those ice sheets, but ice sheets are 2 miles thick. You can't melt that in 2 days or 2 years or 20 years. So a lot of that ice is going to be melting for centuries to millennia, which means sea level is just going to be going higher and higher and higher. And I think that'll be the longest lasting legacy of what we're doing today is, unless we figure something out, sea levels are going to be rising for the next, it sounds wild, but it's just basic physics here. They're going to be rising for the next 1,000+ years. Yeah. Which is pretty challenging.
Exactly,
Yeah.
and especially when you look at the burgeoning population around the world. This is going to be a lot of difficulties, but and maybe they will come up with some way to pull this carbon out of the atmosphere, cleverly,
Right.
or send us all to Mars or whatever.
Yeah.
But in any case, you are now, what's your next project in terms, are you going to save us all from this mess? Or
I wish I was. I think, what I do is my mom always says that, oh, you'll figure it out.
Yes,
I always say,
you're
well,
a scientist.
You're a scientist, yeah. Though I think what I do, unfortunately, is I diagnose the problem. I'm sort of the doctor who diagnoses but I don't have the cure.
You don't have the cures.
Yeah, so I'll keep looking further into the problem, better
Right.
understanding what to expect of it, where it will go. What are the sort of the thresholds, the tipping points, what's on the horizon? I'll keep digging into that.
Yeah. Are you in the field this summer or anything, and what are you looking into?
Not too much this summer. A little bit of a reprieve this summer. Last summer I was
Okay.
in quite a bit. Next summer I'll be back more. But I guess for field work these days, it's largely that project in the Arctic.
Yeah.
Going caving. So hopefully I'll get back up there to do some more of that. And let's see, another project now that I'm just beginning to look actually at, we're talking about melting ice sheets, collapsing and raising sea level.
Yeah.
So I'm starting a project now to do that actually right here in our backyard in New England, where we have big mountains that were poking up into the ice sheet as it melted away during the end of the last ice age. And so I'm climbing up and down these mountains to kind of go measure bathtub rings to figure out when and how fast that ice sheet collapsed in the past.
I see.
To get a handle on how fast and what drives an ice sheet to collapse when
Exactly.
you have a warming climate like today.
Yes,
Yeah.
right. And this is an interesting area probably to be doing that along the East Coast like this.
It's great.
Well, I
Yeah.
wish you the very best in your career. It's wonderful to hear this very comprehensive approach to things, and I hope you'll be talked into writing a book for the public at some point. Try
That would
to
be
work
great.
on that.
That'd be great.
You should do. I
Yeah.
can see this is going to be a need, actually, that the scientists have to try to do this to make this stuff comprehensible to people who are not specialists in these things,
Yeah, I think you're right.
Okay, but I thank you very much for talking with us,
You bet.
and best of luck.
Thanks. It's been fun.